With that said, I would like to introduce to you Professor Marla Geha, who is a professor in both departments of physics and astronomy at Yale University. And before she started at Yale, she did her PhD at UC Santa Cruz, was a Hubble Fellow at Carnegie Observatories and a Plaskett Fellow at HIA in Victoria. And besides being full professor, Marla is also the director of Yale Telescope Resources, the faculty director of the Research Experience for Veteran Undergraduates program, and on the board and the lead of the curriculum developing for the Warrior to Scholar program that tries to bridge the gap to college for US military veterans. And Marla has received numerous awards and is featured in popular articles and is also very involved in bringing science to the public. And in her own words, Marla uses the world's largest telescopes to study the smallest galaxies. And today she will tell us about that and about the Saga Survey. Take it away, Marla.
Awesome. So let's see. I need to share my screen. There we go. Let's see. Do you see my screen? You see it?
Yes.
Okay, great. Awesome. Welcome, everyone. This is both different in good ways and adjustment ways. It is nice to be able to both give colloquium and teach at the same time, and to be able to do both is a real pleasure. I'm also delighted to share with you the results from the Saga survey. We are nearing the end of a very long saga. This is a project that was started, I think the first emails were sent in 2012. And has slowly gained momentum. We just had our second data release just a few weeks ago. We received the referee report for that second data release this morning, actually. And we are just realizing we have a couple of observing runs recently that we will be able to finish this survey by the end of next summer. And so we're super excited. And so this is a bit of a preview for results from that survey. And before we get moving, I wanted to highlight one of my collaborators. It's a fairly small team. In fact, the people that you see on the slide are the team. Yaoyun Mao has been incredible in terms of pushing the survey forward and leads the second data release paper. Okay, so just as way of introduction, I typically, often my other half of my research talks and focuses on the satellites around the Milky Way galaxy. The satellites around the Milky Way provide wonderful constraints, both cosmology and galaxy formation. We've been finding more and more small, ultra-faint galaxies. The last I looked, the count is up to 60-something satellite galaxies around the Milky Way. And the other half of my research group studies these galaxies in great detail. We measure the kinematics of stars in these objects to try and measure their total masses, understand their dark matter content. We can use the number of satellites around the Milky Way to test cosmology. Like say if dark matter was something different, like a warm particle, we perhaps can put constraints on the number of satellites around the Milky Way. Number of satellites around the Milky Way provide constraints directly on dark matter properties. And we can do a whole lot of things, look at metallicities, gas content in all these galaxies. And the proximity of these satellites allows us to do all these amazing studies. We can do similar studies around M31. So the satellite system around M31 now contains something like 30 satellites. And we can do similar metallicity, dynamics, constraints, but we really can't get much further than that. We can do individual stars out to maybe a megaparsec or two. And so this leads to a problem, and this is the genesis of the satellite, the Saga survey. And that is, we learn and we infer a lot from the satellites of the Milky Way, but are the Milky Way satellites representative of a true Milky Way, sort of a perfect Milky Way? And so sort of as an example, let me just show you the luminosity function. So this is the luminosity function, so fainter objects over here, and the cumulative number on the y-axis. And the orange, oh wow, the purple contours represent, if you do numerical simulations and you look at a single Milky Way host, that's the 95% scatter in the cumulative luminosity function of satellites. And so it's fairly broad, comparing that to the Milky Way, which are the data points. Again, because the Milky Way at the bright end has 1, 2, 3, 5 satellites, the statistics are pretty bad here. In simulations, we can ask what you would get in terms of luminosity function if we had 10 Milky Way hosts, and that's the red region. And then we can also ask if we had 1,000 Milky Ways, and that's the blue. And there are in fact error bars on that blue luminosity function, although you can't see them. We really can't do the same for the Milky Way or for the observations. And indeed, until maybe 5 years ago, really just the Milky Way was it, and that's all that we had satellites around. And so in the last couple of years, people have started to characterize the luminosity functions around nearby Milky Ways. And you can imagine there's sort of as a choice between going to just a few Milky Ways and looking for satellites down to fairly faint magnitudes, or getting statistics, but for statistics you have to go to brighter magnitudes. And so Saga chose, we chose to go for statistics. And so we decided many years ago to try and characterize the satellite populations around 100 Milky Way analogs. And that number 100 was chosen roughly so that we could get luminosity functions that had fairly well-constrained luminosity functions. And if we want to get 100 objects, that sort of pushes us to a magnitude limit that I'll talk about observationally right about here. So we're looking at objects, at satellites down to about -12 in luminosity, which is roughly in stellar mass, something like 10 to the 6, 10 to the 7. For the Milky Way has 5 satellites in this regime. So it would be the Magellanic Clouds, Sagittarius, Fornax, and Leo 1. And so I will talk about the observational things that push us once we have made this choice, but I want to show you what this choice means in terms just sort of visually. So this is a cool graphic that Yao put together. So on the x-axis is distance, and the y-axis is sort of roughly the number of satellites you might expect in a system. So here we have the Milky Way, so the local group. The Milky Way has something like 60 satellites, M31 something like 25. If we move farther out into the local volume, let's say out to 20 megaparsecs, we can continue to find satellites. Rather, in the Milky Way, we're able to find them just based on the overdensities of resolved stars. As we move farther out in distance, like say 20 megaparsecs, we can do things like tip of the red giant branch to find satellites, or surface brightness fluctuations, that is just looking at like the bumpiness of a satellite to determine its distance. And out at these distances, you can find satellites around a Milky Way down to something like say 5 to 8 satellites per host. And then on the other side of this, we can use the Sloan Digital Sky Survey. So Sloan, we can get satellites around Milky Ways out to about 200 megaparsecs. That is constrained by the full satellite, by the full spectroscopic survey. The spectroscopic survey went down to 17.7. And you're getting sort of roughly 1 satellite, 1 LMC basically per host. Saga lies right in the middle. So here we are, we're somewhere between 25 and 40 megaparsecs. We are able to detect down to our magnitude limits, roughly 3 to 5 satellites per host. We are in the middle in between various different detection methods. And so out beyond about 20 megaparsecs, we cannot use surface brightness fluctuations. We're too close to be able to use reliable photoz's. Photoz's don't really start working well until about 100 megaparsecs or so. And so the Saga survey is basically pushed to doing kind of brute force spectroscopy to try and find satellites. And that's what we did in the first part of the survey. And now we're becoming a little bit more sophisticated. And so I'll walk you through that. Okay, but to observe 100 Milky Ways, we need to get out to a volume of roughly 30 megaparsecs. So that's just, if we define a Milky Way, and I'll define that in the next slide. If we define a Milky Way as being in some luminosity range and some environment range, we need to get out to about 30 megaparsecs to have sufficient volume to get 100 Milky Ways. At 30 megaparsecs, the virial radius of the Milky Way, which we define as roughly 300 kiloparsecs projected, is equivalent to about a degree on the sky. That's gigantic, right? That's like 2 full moons. At 30 megaparsecs, if we want to get down to -12, that's equivalent to roughly an R of 21, which is well matched to spectroscopy with large, sort of 4-meter class telescopes. So putting that together, within 1 degree, there are a few thousand galaxies down to an R of 21. And so I will come back in one slide to how we actually sort through all those galaxies. But first I want to take a minute and just discuss how we define the Milky Way. So ultimately we'd like to define the Milky Way as being some dark halo mass, but we can't observe its dark halo mass, and so we need to do something else. And so what we decided to do, and this was a choice, is we define the Milky Way as having a halo mass of, let's say, 1.6 or so times 10 to the 12th. And then we just look at sort of a canonical stellar mass, halo mass relationship and ask, what is the plausible region in stellar mass as proxied by its K-band luminosity where that halo mass could reside? That is, here we have a bunch of N-body simulations. This is halo mass at a halo mass of 1.6 times 10 to the 12th. We ask, what is the range of K-band luminosity? And so we are looking at stellar masses, K-band luminosity of hosts in this range between -23 to -24.5 or so. And so we define a Milky Way as having some K-band luminosity. We also define it as a particular environment. And so we ask that a Milky Way be outside of a big group. So it's not inside of the 2-mass group catalog. And it also cannot have a galaxy that is its magnitude or 1.6 magnitudes fainter with inside its virial mass. That is, we don't want to have 2 Milky Ways inside of a virial mass, and that 1.6 is defined by that range in stellar mass. And then we have some practical considerations. We don't want the object to be right in the middle of the galactic plane because there's a bunch of super annoying stars. And so that's how we define our sample. And so we define this survey basically into 3 stages. In our first stage, we wanted to do basically complete spectroscopy of all of the galaxies inside of the virial radius using some fairly simple color cuts where we knew we would get all the low redshift galaxies, all of the satellites we were interested in. In stage 2, we are going to design sort of more efficient targeting strategies. And then stage 3, we're going to do this super efficiently. And so we accomplished stage 1 in 2017, where we observed satellites, complete satellite luminosity functions around 8 hosts. We were very proud of those 8 hosts. We had 12,000 redshifts to find 27 satellites. And so in the words of my super esteemed colleagues, this was the least efficient survey ever. In stage 2, we have gotten a lot better. So in stage 2, we basically had a training set from stage 1 to be able to design cuts in both color and surface brightness to be able to do this more efficiently. So stage 2 was just published last month and is on AstroPH. So here we've got 36 hosts. We have found 127 satellites. But you'll notice that although we more than quadrupled the number of hosts, we did not more than quadruple the number of redshifts we needed to take. And we are well on our way to stage 3, where we're going to get 100 hosts. And in fact, preview to the end of the talk, we're now up to 75 hosts with complete satellite luminosity functions, which is super exciting. All right, so stage 1 versus stage 2, just visually, there are 133 galaxies which satisfy all of those Milky Way cuts out to our distance cuts. Here they are on the sky. You can see the galactic plane kind of cutting through here. This is a RA and DEC projection. And the open circles, or all the circles, are Milky Ways, but we need to have imaging. We need to be able to target our galaxies. We need to have colors and sizes of our candidate satellites. And so in stage 1 in 2017, we only had access to SDSS coverage. And so that's those blue dots. And we were able to complete these 8 red objects. So the 8 red hosts where we had SDSS imaging. In stage 2, we have done 2 things. So we have both here increased the number of complete satellite systems, so that's 36, but we've also adopted both DES imaging and legacy survey coverage, which is both much deeper than our survey limit. So it gives us more accurate photometry and gives us access to a much larger part of the sky. Okay, so just kind of again looking at this. So here is one of our hosts. This is the circle is our full virial radius. Our Milky Way analog is sitting at the center of this circle. The blue dots are every galaxy down to our limit of R of 21. And so it's about 2,500 galaxies per square degree. And that's a lot. So you can actually see there's a galaxy cluster sitting right there. Where are we headed? You know, we're headed way over here. This galaxy, or this Milky Way, has two, oops, sorry, don't see that yet, has 2 satellites, right? So this is something like 4 satellites per square degree. So in stage 1, we did very simple color cuts. We did a color cut in G, R, and I, where we were absolutely certain that we were only getting rid of higher redshift higher than about 0.1 galaxies. This got us down to a target magnitude of 1,000 galaxies per square degree, and we just did it. We got spectra for all of those galaxies. And we were doing this with multi-object spectroscopy. So in particular, we're using the AAT, 2DF in AAT, and the MMT hectospec. And I'll talk a little bit about, we were also doing single slit follow-up for the faintest objects. So in stage 2, you can see that we've now really reduced the number of objects we need to get. So we're now down to about 200 galaxies per square degree, and we are still confident that we are not missing any low redshift potential satellites. Okay, so we'll talk a little bit about how we did that. Just a note, again, doing spectroscopic follow-up takes a lot of work, and we really rely on these wide field, 1 degree, 2 degree field of view instruments that have multi-fibers, so we can observe multiple hosts per night. And I'd love to talk about the spectroscopy. That's where we put in most of the work, but we're not gonna. Great. So here is the redshift distribution of our galaxies. So this is redshift on the x-axis, and this is the number of galaxies per square degree for a particular cut. So the red is basically all of the redshifts with any kind of color in our fields. The light blue is doing these GRI color cuts. And so for stage 1, our median redshift was about redshift of 0.2. And now our improved color cuts and surface brightness cuts, we have a median redshift of about 0.1. And just kind of zooming in on the redshift of interest. So all of our hosts are at redshifts of like 0.01 or 0.00, whatever. This spike in the redshift distributions, this is just a zoom of the left panel. Those are our satellites. That's our overdensity of our intended sources. And you can see that out to about 0.02, our cuts are complete. So this is a good, these cuts are interesting in terms of, let's say, a big redshift survey like DESI, trying to look for low redshift galaxies. All right, what are these cuts? So these are the cuts that we apply for our the main targeting cuts in stage 2. So this is surface brightness, effective surface brightness of our galaxies, and apparent magnitude on the x-axis, and then color, and again, apparent magnitude. And so our primary cuts are galaxies have to be fairly low surface brightness, but as a function of apparent magnitude, and somewhat blue. But what I'm plotting here are not only all of the satellites that we've observed, but also all of the low redshift galaxies as well. And so we search for satellites essentially in 2 ways. And so the first one is that we require complete spectroscopy inside of Vero radius, inside of these cuts, but we are not convinced that these cuts are perfect yet. And so we also do discovery mode, where we continue to look at galaxies outside of these regions in every pointing, just in case we screwed up in some way. So far, with our 70-something hosts, we have found no low redshift, no satellites outside of our primary cuts, but we will continue to look in these regions. So this is just, again, a bit of a visual for what we define as a complete galaxy or complete host. So we require a galaxy, a Milky Way analog to have 80% completeness in those primary cuts that I just showed you. So this is percent completeness, and this is the number of objects that we have, redshifts that we still need. And so here, this is how we define that 36 host sample. And again, a lot of these points have now moved into the red where we have spectroscopy. Just kind of breaking down the completeness. So this is the spectroscopic coverage as a function of absolute magnitude inside of our Vero radius, assuming that all of those objects are at the same distance as the host. And so here what we see is that for our host, those are the green things, we are absolutely complete. That is, we have redshifts for every single galaxy inside of our cuts down to about an absolute magnitude of -15. And then as we go towards fainter absolute magnitudes, we're still doing quite well, you know, sort of 90% down to our limit of -12 in absolute luminosity. And the yellow is just to point out that that is a spectroscopic coverage before Saga. So that is that the Sloan Digital Sky Survey, although it is complete down, you know, nominally complete down to at these limits, kind of -16 or so, -17. In fact, there are missing objects in these fields from Sloan even. Okay, so stage 2, the paper, we identified 127 satellites around 36 hosts using these cuts. Interestingly, 3 of those complete systems actually had no satellites. And here I'm going to pause. This is my red bar to say pause and take questions. But for a minute, we're just going to stare at this slide, because I could stare at this slide for the entire talk. So these are all of our satellites. They are organized by host. So each kind of color region is one host, one Milky Way analog. Within a host, the satellites are organized by decreasing luminosity. The red dog ear on the top of each indicates whether an object is quenched or not, that is whether we see H-alpha emission. And then the blue dog ear is if it's below our satellite luminosity magnitude. So the satellites are very pretty. There we are. So we'll kind of go through kind of the highlights of the results in the paper. And I also urge you to go to the sagasurvey.org where we go through the highlights of the results as well. So this is the luminosity function and the number of satellites as a function of host luminosity from paper 1, where we had 8 satellites. 8 hosts. So you can kind of see there is starting to be some, you know, the satellite luminosity functions are fairly different. And the number of satellites as a function of host luminosity looks like there might be a trend, but it was kind of hard to say very much in paper 1. So here are the same 2 plots from paper 2. So first of all, we are populating the rainbow. And my hope is just this in the 3rd stage, that this is just a complete rainbow plot. But what you notice is that we have satellite systems where we have 8 or 9 satellites, and similar systems where we have 0 satellites down to our limits. And so sort of a fairly basic conclusion here is that there are between 0 and 9 satellites per Milky Way host. But what's quite interesting is, so the Milky Way is this dotted dash black line, M31 is the longer dashed line. The number of satellites correlates roughly with host luminosity. So you can see there is some trend here, but the trend is actually not super strong. And in fact, what's quite interesting is the number of satellites correlates more strongly with the presence of an LMC. That is, if a host over here has a bright satellite, an LMC or brighter satellite, it tends to have more satellites. That is, the red luminosity functions, you know, they tend to organize by color. And so there's a stronger correlation with brightest satellite magnitude than number of satellites or host magnitude, which I think is quite interesting. The Milky Way is right here. And we find that the Milky Way luminosity function is consistent with being drawn from the Saga luminosity function. That is, if we drew the Milky Way out from our population, we would draw the Milky Way with some frequency. And so the Milky Way seems to be fairly consistent with what we're seeing in the sort of the greater environment. I do want to make a quick point. There was a paper, and I don't have the reference right now, sort of on purpose, just about a week ago, saying that the Milky Way luminosity function was quite different. I think it was at like 19 sigma from the nearby field luminosity function for Milky Ways. And if we just took the average of our luminosity function and asked if Milky Way is different, indeed you would find that it is fairly different. But we also have to account for the fact that we're seeing this huge scatter. And so not only do we see the Milky Way being drawn from, being drawn from the Saga luminosity function, the Saga luminosity function has a lot of scatter. And so those are sort of 2 different conclusions, right? We have the Milky Way being consistent, but that there is also a lot of scatter in the luminosity function down to our limits. This is true for the radial distributions as well. So now we're looking at the projected distance of a satellite, and this is the cumulative distribution. So this is a cumulative distribution of satellites in projected distance away from the Milky Way. The green line is our average Saga luminosity, Saga radial distribution. And the red, so this red dashed line, is the same for the Milky Way. And then the red sort of boxed region is, if you imagine viewing the Milky Way from a whole bunch of different places, that's what the range in the radial distribution of satellites would look like. And so at first blush, it would appear that the Milky Way radial distribution is quite different from the average Saga distribution. However, if you now take, let's say, the 25%, that is, the Milky Way distribution is more concentrated than the average Saga radial distribution. But if you then look at the green line, this small green line is the 25% most concentrated Saga systems. In fact, the Milky Way is fairly consistent with our more concentrated systems. Another way of saying that is the radial distribution of Saga satellites, while it is less concentrated than the Milky Way, we can account for that just based on host-to-host scatter within the survey, within the sample. So there's a lot of scatter in the radial distribution. That said, the Milky Way is on the more concentrated edge of our distribution. Okay. Moving on and talking about the properties of the satellites themselves. And I have to say, this next one is what I get the most excited about, but there we are. So we looked at the quenched fraction of satellites. And in paper 1, we found this kind of weird thing that only one of our satellites out of our 26 were quenched. That is, that we didn't see H alpha emission in our spectra. So here I'm plotting the absolute luminosity of satellites. Their G minus R color, and then it's color coded by the equivalent width of H alpha. And here you might, and we were super worried, like you might be like, oh man, you definitely are missing quenched satellites. However, in the field, we were finding lots of quenched objects. The signal to noise in these spectra are actually quite high. And so we're seeing, even in our star forming satellites, we see absorption lines. And so I was pretty convinced we weren't missing quenched satellites. And so in paper 2, this result holds. Sorry, before I go to paper 2, so in the Milky Way, you would expect 2 out of 5 satellites, the Magellanic Clouds, are star forming. And so Saga was much more quenched than in the Milky Way. In paper 2, we find that 18 out of our 127 satellites are quenched. But we notice that most of those galaxies, most of those quenched things are faint. That is, most of our quenched satellites are on the fainter end, or are less luminous than -16, which is maybe the opposite than what you would expect if this was a bias, that we were biased against quenched satellites. You might expect more of the quenched things would be faint or bright and intrinsically more luminous. And so the quenched satellites are found preferentially at lower stellar mass. What you can't see here is that the 2 objects that are quenched that are brighter are actually very, very close to the host. So they're both nearer to the host and are at lower stellar mass. And so we can put this together in a little bit better. Here is the quenched fraction, which Chich knows quite about, and we've been thinking about a lot in a different context, as a function of stellar mass. And so here is the field quenched fraction of isolated galaxies. Years ago, we found in the Sloan Digital Sky Survey this kind of amazing thing that for very isolated galaxies, we found no quenched galaxies in the field. That is, below 10 to the 9 out of 3,000 isolated quenched low mass galaxies, none of those things were quenched. They were all star forming. In the Milky Way and M31, we see that the quenched fraction increases as you go to lower stellar mass. That is, below, in the Milky Way, about stellar mass of 10 to the 8, that is below the SMC, all of our satellites are quenched. They are not forming stars. The Saga survey, we see something a little bit different. So the green points are the quenched fractions as measured. And you can see the quenched fraction is quite low, down at only about 20%, but increasing in the same direction. The green error bars are if we missed, it's a conservative calculation that if every single satellite that we missed and we didn't get a redshift for, if we assume every single one of those is quenched, which is probably not true, but let's say they were all quenched, that is the maximum quenched fraction that we would get. That is, if we got redshifts for every single object we're missing and we decided every single one of those was quenched, that is the quench fraction we would calculate, and it still wouldn't get us up to the Milky Way M31 quench fractions. And so overall, the quench fractions for satellite systems around Saga are lower, that is more star forming than the local group. And this is actually interesting if we compare to simulations. And so I should probably get a cleaner plot of this, but this is simulations from recent ones coming out of Alison Brooks's group, looking at the quench fractions. And indeed, this is their red, is their predicted quench fractions. You know, they are not quite as sharp and not quite as severe as we're seeing. Let me rephrase that. They're similar to what we're seeing in the Milky Way M31 because probably they're tuned to reproduce some of that. In Saga, we're seeing lower quench fractions. And so that's sort of somewhat interesting. I'm going to just speed through this. This is the properties of the satellites themselves. Here is just to say that we do see some objects that are nominally defined as ultra diffuse galaxies. The stars are all of the Milky Way satellites. And this one is, these plots are really just to say that we are in the same region in terms of surface brightness, size, and color as the Milky Way satellites in the same luminosity region. So the Milky Way absolutely has lower surface brightness objects. The ultra diffuse or ultra faint galaxies are way lower surface brightness, but we aren't interested in those low surface brightness things. We're only interested in things that are fairly bright. So Leo 1 has a surface brightness that is similar to all the objects that we're seeing in our survey. Okay, yeah, I'll talk about planes of satellites for a second. I have a little bit of time. So we have looked at whether or not we can see planes of satellites or co-rotating planes in the Saga survey. And so the way we define this statistically, we can't, we only have 3 or 4 objects or maybe at most 9 objects per host. And so we look statistically and we ask, if we had a rotating, co-rotating plane of satellites, you would expect that satellites on opposite sides of a host would have, a co-rotating signal. And so here we're defining an opening angle of a satellite and ask whether or not it is rotating or co-rotating or anti-rotating. If you had a cold rotating plane, you would expect this plot to look kind of U-shaped. You would expect to have peaks at 0 and 180 degree opening angles, and then sort of random co-rotating, non-rotating right in the middle. The blue is what you find with Sloan, and the green is what we find if we mimic Sloan. So Sloan was able to look at, for satellite pairs, out to 150 projected kiloparsecs. And that's what we do if we have the green dots, but we're able to go out to 300. And so that is the gray, the gray is the SDSS. That's the blue contours, the blue region. And so we don't see any signal of this kind of U-shaped region in this diagram. But we're still pretty much noisier than SDSS given our statistics. What we do see that's kind of interesting is we see a hint of satellites coming in together with the same velocities that are also spatially together. That is, we're seeing some hint of satellites coming in as groups together, like an LMC-SMC pair. We don't have really great statistics on that yet. It's only a handful of pairs, but when we get to the larger sample, I think that will be interesting. Okay, my last big science result here is looking at the number of satellites and comparing that back into simulations. And so the dots and the stars are the Saga observations. And so here is the number of satellites, and this is the number of hosts that has that number. And so the stars are the observed number. So here we have 3 hosts that have 0 satellites, but we know we're missing some satellites and we can account for that. And so in fact, we think we're actually only have 2 systems where we have 2 satellites. The contours are an N-body plus empirical satellite model from Ethan Nadler and Yayu Mao. And so projecting into the Saga space. And what's kind of exciting to me is I always thought that the systems where we had no satellites was bad. That is, we must be doing something wrong. But in fact, in the simulations, there is a fairly large range. And it seems like the Saga range is in fact agreeing right now with the empirical models that we're comparing to. That is that the Saga satellite systems are broadly in agreement with predictions from CDM and semi-empirical models. So that's kind of cool, but obviously stay tuned. We'll be able to do a lot better with a lot more statistics. And so I have 2 minutes, maybe 3 minutes, just to summarize and look at the future. So here we are, stage 1 and stage 2. What are the prospects for stage 3? So getting to this goal of 100 Milky Ways, where we can really do things like we can start to talk about local group and, you know, split things out into local groups versus isolated Milky Ways, split things out into conformity, blue satellite, or blue host, red host. And so here is the published number of complete satellite systems on the sky, 36. This makes me so happy, and that's why I did this crazy animation. So this is where we are today. So in the summer, or beginning of summer in 2020, we had 36 complete hosts. We're now up to 72. And I'm just going to show you why. So that's my TV room. We had a fair amount of AAT time over the summer. And obviously there's some things going on that prevents us from traveling. And so AAT was amazing to work with us so that we could actually observe from home. So this is a Linux box that I borrowed from work with 4 computer screens running off of it. I've got 2 laptops. I totally ran out of furniture. I didn't run out of bandwidth. I ran out of furniture. And so it's been crazy. You know, kids are home. There's no school. I'm observing. It's been super amazing and awesome and ridiculous. But we're now up to 72 hosts. We are submitting proposals actually tomorrow, NOAO proposal deadline, to try and fill out the hosts that are in the spring sky, so those green objects. And so we have a very viable path to completing the survey by the end of the spring. And so hopefully we will be able to publish phase 3 by the end of next summer. I just want to totally thank my team members. I have to say science is fun, but doing science with good people is better. And it's been a real joy to be able to work with my team and just get this awesome survey out. So with that, I'm going to leave the conclusions, all of which we have talked about, and take questions.